Welcome to Hot Chips 29. Session 8, Architecture.
Good afternoon. I'm Dilip Bhandarkar and from Qualcomm, and I am the session chair for the architecture section. We have two talks in this section. The first talk is a 400 gigabits per second multi-core network processor, and the speaker is James Markevitch. He's a principal engineer at Cisco. He's been working at Cisco since 2001, and is responsible for architecture of high-end routing chips. Before Cisco, he's worked on OS kernel development, CAD software, processor, and networking chips. Please welcome Jamie.
Okay, so this slide, I think, has no typos in it. The word neural is missing on purpose. So switch gears, no Macs, no FP16s. And legal, you looked at it, you clearly agreed to it. Now, something that's important, if I can get the clicker, please. Something important is that this work was done by a large team, geographically distributed, multiple places in the United States and multiple countries. Some of the things that I'll be talking about, it's other people on the team who are really the experts. So, the clicker. There we go. Thank you. Yeah. This box? Okay, so background on a distributed router, which this chip is really oriented towards. This is the last background slide. It's not a tutorial on network routers and switches, but the concept of a distributed router is that you have, as you can see on the diagram on the right, a bunch of network processors. One side of the network processor is facing towards the line, which is the where you plug your fiber or electrical Ethernet cables into. And the other side, there's a fabric. And so one might build a chassis with tens of terabits per second of bandwidth, and each network processor is responsible for some number of interfaces, and they all communicate with each other across the fabric. Now, the reason that's important is this slide says 800 gigabits per second of bandwidth going through this chip. This means there's 400 gigabits per second going from the line to the fabric, and there's 400 gigabits per second of packet data going from the fabric to the line. So there's 800 gigabits total flowing through the chip. Now, I refer to this as a 400 gigabit chip. Some people would call this an 800. People even call this 1.6T, since there's 400 in on each side, on either side, and 400 out on either side. If you notice on the schematic representation of the chip, in addition to the interfaces on the left and right-hand side to the fabric and line, on the bottom, there's a whole lot of SerDes going out to DRAM, and I'm going to talk about that toward the end of the presentation. This is a custom-designed DRAM, serial-attached DRAM chip. There's a total of 6.5 terabits per second of I/O bandwidth on this chip. So, as you can infer, a large percentage of that is to the memory. So about a quarter of it, give or take, is packet data coming in and out, and the other 3/4 is to DRAM and a serial-attached TCAM. Now, in addition to that, we have an integrated traffic manager, which I'll get to later in the presentation. So the overall architecture is that data comes in, and let's say data comes in from either the fabric or the line. It's stored on chip while it's being processed. So every packet that's currently actively being processed is stored on the chip, and that allows the processor to access not just headers, but deeper into the packet for features that require deeper access. There's the processor array that I'm going to talk about in a lot more depth. We have a number of hardware accelerators that are specific to networking. Some, I guess, would be even other general purpose processing. And then a traffic manager that I mentioned earlier. So typically, packets come in from the left-hand side, the MACs, which are the media interfaces to fiber or electrical. They're stored entirely on the chip. They are then processed. So the processor array receives, a notification that a new packet is there. It's able to look at the packets as deeply as it wants, and many packets, in fact, up to 2,688 can be processed in parallel on this chip. The processor array, in addition to being able to go and access the packets, can go out and access external memory, because this chip is designed to support large tables where on-chip memory is insufficient. It can also access hardware accelerators. There are some features in networking that require global data, and in order to do that, all the individual processors have to go out and coordinate or take advantage of a special purpose piece of hardware that can accelerate some functions. Eventually, once the packets have been processed, and this is the case of going from the line to the fabric, the packets go out to the fabric and eventually find themselves in a different network processor where they're then further processed before they're sent out to the line. Then the flip side is that side, the egress side, which is where packets go from the fabric. Mostly a repeat of the ingress case, except that after the packets have been processed in this particular architecture, they are put into a traffic manager. Now, the traffic manager implements things like quality of service. It knows that if one customer has said, they're paying for X amount of bandwidth, that they get guaranteed that bandwidth. If other customers aren't paying for some amount of bandwidth, they may be sharing it. It fairly distributes the bandwidth among those customers. That's the types of things that a traffic manager does. So in this architecture, after processing, packets are copied off the chip, managed by the traffic manager, and then eventually go back outside the line. There are a variety of architectures. This happens to be the architecture for this chip. Now, the processing model is that something called run to completion. Run to completion means that, unlike the systolic array we heard about a couple of talks ago, where you have a bunch of things going on, each stage is doing a different part of the processing. In this case, it looks just like a traditional programming model. To process a packet, one writes a little piece of C code or a big piece of C code with all of the features. When a packet is received, the processor runs, and it executes that thread executes that code just as with any general purpose processor. Now, in our case, we have 672 processor cores on this chip, and as I mentioned, it can be programmed in C or assembly, including a full stack, full memory management unit, things that would be very familiar to most general purpose programmers. So going into one of the 672 cores, there's a pipeline. In this case, for this particular chip, it's a H-stage pipeline. It's non-blocking, so the pipeline doesn't stall. The pipeline is fed from an L0 instruction cache, which is small, just enough to keep the pipeline full, to hide the latency out to the L1I cache, and to handle very small kernels of code so that the pipeline can be full. It's this particular chip is 4 threads per core, and there is a scheduler that's pointed out on the slide doing round-robin scheduling on a cycle-by-cycle basis, picking an eligible thread and sending an instruction down the pipeline. And so necessarily this implies that there can be multiple threads executing simultaneously within the pipeline. Register file is, of course, per thread. L0 dcache per thread, a two-way set associative. There's a MMU that is software managed, again, per thread. And the box that I've described, a request generator, as shown on the previous slides, there are a lot of external there's a lot of hardware external to the processor array itself. There's memory, there is packet storage, and there are hardware accelerators. And this handles both misses as well as explicit requests to go out and send a message to one of these external hardware acceleration units. So then popping up to the next level, processor cores are arranged in clusters of 16 processors. They share a somewhat larger L1 instruction cache and what we call a table lookup unit with, for the purpose of this talk, we'll call it an L1D cache. Basically, this is a unit that accelerates table lookup type functions that one encounters in networking. And so there are hash lookups and a variety of other lookup mechanisms. This not only accelerates those, but it also caches them and eventually can convert them into raw memory accesses that can go outside of the processor array. And each of those are multi-way set associative caches in the cluster. And then pushing out the processor array itself consists of, in this case, 42 clusters. Some of the cluster, there are L2 instruction caches that are shared by, in this case, a third of the clusters each. Those, as well as the clusters, can all send messages out through this interconnect to the rest of the chip. And so everything eventually, to get out of the processor array, goes through this interconnect. And I think when I did the calculation, there's something like 9 terabits of bandwidth. It's a bipartite in-order interconnect. So something to point out, this is running at a gigahertz. The processor array is hand-placed, and hand, of course, means custom, or automated tools that we've generated. Nobody sits there and tweaks every single little thing, but there are a lot of hints that are put in and a lot of custom tools that were created to help do this. And so it does not use a standard automatic place and route methodology. So just an example of some of the hardware accelerators. One common thing that's done in networking is prefix lookup. And so everybody's familiar with 192.168. Whatever, in this case 0.123. Now the unfortunate thing, or fortunate, I guess depending, the way the internet evolved, there's no hierarchy to these, or minimal hierarchy to this numbering. And so the obvious algorithms that one would use for a hierarchical mechanism, or for a hierarchical addressing scheme, don't apply in this case. And Cisco has a variety of different algorithms. Everybody in networking has a variety of algorithms to try to overcome this. But this makes for an interesting piece of hardware, and it warrants its own, being its own accelerator on the chip, and implements our proprietary algorithm to basically resolve for a given address where should this packet go to next. TCAM lookups, hashing, range compression. These are, an example is you may say, configure a router to say, I don't want some subset of traffic that comes in to get out because this represents a DDoS attack, for example. That would be put into one of these tables, and there are a number of different lookup mechanisms that are designed to optimize the amount of space that is used by these tables and still be able to efficiently look them up. Those are examples of global accelerators. Another thing is counters, and I think I'd say here rate monitors. These counters, an example, is frequently in places in the internet, it's very important that a customer can audit exactly how much data went through some place. They may have service level agreements with their customers. They need to prove that what they have sold or contractually agreed to has been adhered to. There are also a lot of debugging reasons to do this. customers of networking gear really want to understand what's happening in their network, even if they don't have to report this to their customers, they need to understand so that they know how to manage and grow their network. The other is packet ordering. What I didn't say is these 2,688 packets that may be all processed simultaneously in these different threads. There's no ordering between the processors themselves. And so you can have packets go to 1,000, or sorry, to, in this case, 400 different processors, let's say, and one of them goes to a memory that's just gets a little slower because of queuing, and so the order in which packets came in, the order in which they finished their processing, may not be correct. There's a special hardware whose sole purpose is to deal with that and to ensure that for what I'll say is a flow, which is a pair of packets that where ordering matters, that they eventually leave the chip in the order that they're expected to leave, that the arbitrary processing doesn't induce out-of-orderness that high-level protocols on the internet would be disturbed by. And the other thing on the chip that I mentioned earlier is the traffic manager. Now, the diagram on the left is intended to show a tree, and for a little background, let's say on this on a router you have a physical port, so you have a 10 gigabit Ethernet or 100 gigabit Ethernet port. Well, that may be split up logically into something that will be deeper in the network that maybe is a bunch of 1 gigabit Ethernet ports, but they sort of look like logical ports as when you're trying to manage the traffic. When you're trying to ensure that a certain minimum rate or maximum rate or sharing rate is achieved on these ports. And below that, you may have end customers. And so, an example is for a cable network provider, there may be, maybe they're serving tens of thousands or hundreds of thousands of customers off of one of these devices. In that case, each of those customers, maybe you've paid for a certain amount of service, you get a guaranteed 30 megabits per second, but it can burst up to 100. That would be contained here, in the description of the customer node in this. Now, not everybody in this room, if they're all in there, not everybody in this room can get that 100 megabits simultaneously. They may get their guaranteed 30, but if everybody jumps on it at the same time, this tree would have to correctly ensure that everybody gets 30, and beyond that, everybody shares a fair share. Now, below that, there's this concept, and this is just one example. There are a whole bunch of different hierarchies that can be created. One might have voice, one might have video, and then surfing. And when your teenager goes and plays whatever he's playing, you don't want Game of Thrones to suddenly, get all of the speckles on the screen. And so those will be put into different priorities, and those are down at the lowest layer in this example. So the traffic manager has to decide for this physical port that maybe is capable of sending 100 gigabits per second, if there's a 6 megabit per second video stream coming through it, how does it get all the way to the top and meet all the guarantees all the way through? And remember, there are thousands and thousands or tens of thousands of customers that are on here. All of these guarantees have to be met. So the traffic manager, in this case, can handle up to 256,000 queues, and it can manage these min rates, the maximum rates, as well as fair sharing. And it does the equivalent of, I think I calculated approximately 500 billion objects are sorted every second, where an object is a packet or a representation of a packet. So it has to do this big sorting algorithm equivalent and meet all these guarantees. So that ends up, we'll see in a bit, that ends up being a reasonably sized chunk of the chip. And as I mentioned earlier, the packets themselves are stored off the chip. So here's like the previous presenter, not an actual die photograph, but the schematic outline of the die. The 672 processors, this chip had 9 billion transistors in it, 363 megabits of SRAM, and the yellow all around the border there is SerDes. So this is largely, the chip is almost completely surrounded by SerDes. There's a little bit of debug I/O and things like that, but all of the connection out to memories and to everything else is via these SerDes. So there are 276 SerDes on there, 643 square millimeter die, and this was done with a hybrid custom flow. So as I mentioned, the processor array is done with a bunch of special tools. It doesn't use automatic place and route. The rest of the die, and so you can see the processor array is about somewhere between a quarter and a third probably of the silicon. The rest of it is done using automatic place and route. And so we've looked at where we get the best bang for our buck here on effort, and that's where we made the trade-off. And you can see the traffic manager is fairly substantial, and the accelerators are fairly substantial amount of die space, even outside of the processor array. So, as I mentioned, there's a lot of memory there's a lot of SerDes bandwidth out to memory, and the reason we have external memory on this chip is places in the network where this goes needs a lot of buffering, more buffering than is going to fit on the chip. And so if you think if you have 400 gigabits going through the chip and you store that for 2.5 milliseconds, you're at a gigabit of storage, which is quite a bit, and our storage requirements are substantially greater than that. So on-die is just not feasible for this chip. The other is where this goes in the network, table sizes can be very large. The amount of addresses that have to be handled, the amount of rules on processing a variety of features. And the way to think of it is every time you add a feature, you're probably adding at least 1 or 2 memory accesses. Now, architecture, everybody tries, is as clever as they can be to try to reduce how many of these accesses have to go outside the processor array, have to go outside the chip. But eventually, quite a bit of it does have to go outside the chip. And so there was a need for quite a bit of bandwidth, quite a bit of DRAM bandwidth on this chip. So we built for a serial attached memory. It is serially attached at 12.5 gig. That was, given the generation when this was designed, that was an appropriate speed. The memory protocol out to this was optimized for networking, and so we looked at what are the what types of transactions do we really do, and the other thing it was optimized for was high random access rate. So this chip supports 1 billion random accesses per second and 300 gigabits per second of bandwidth using SerDes, and we put an asymmetrical number of SerDes, so you can either use this device like a pure packet buffer, where the number of reads is approximately equal to the number of writes, and I say approximately because there are silly things like multicast, or table-type lookups, where you don't tend to update them very often. Maybe you update something 100,000 times a second, but you read it hundreds of millions of times a second. And so the chip allowed us we designed the chip so it could be used in either type of application. So here is a picture of it. It was implemented using 2 die. There is a memory die, a 30 nanometer DRAM die, connected to a logic die in 28 nanometer that contains all of the SerDes as well as the BIST and complete understanding of the protocol that converts it down into a DDR type of interface out to the memory die. Power has been really, really important in these types of applications, and so this uses very low voltage I/O. We worked with our vendor to ensure that they had some drivers and receivers that would give us very effective communication and reliable communication at a low voltage. And so we pushed on this to keep the power exceedingly low if we could. So before I go to questions, I wanted to bring up one picture that I wasn't able to, you want to grab that one? Yeah. to see it there. Ah, there we go. Yeah. So this.
Yeah, it's not up on the screen yet.
Okay.
Oh, it is now.
Yeah.
Okay.
So this is. It doesn't look. It looks okay there. But the people backstage were oohing and awing over a big die. When I started in chips, and probably most of us started in chips, they would fit over your fingernail, and these are pretty huge. So, and I didn't tell my colleagues that 28 years ago I dropped a wafer. So, anyway, so stuff's real. It's out there. It's in production, and hopefully all of you get to see wafers for the things that you've designed. So, thank you.
Thank you, Jimmy. We've got time for a few questions. Please state your name and affiliation.
Michael Shea, UC Berkeley Extension. Question here is, in the context of SDN and NFV, are there any features on this particular processor that have been tailored to further enhance the ease of usability for those application software?
It could be used appropriately for that. They were not explicitly put in. This was architected. NFV didn't go by that name when this was architected, but the concept of it was well in mind. And so there's quite a bit of processing power, or quite a bit of processing capability that could enable SDN, NFV type of things. And then it's up to what actually gets productized. But yes, the general purpose nature of it and some of the accelerators we've put in could allow that type of thing.
Thank you.
So Nick Dubé, HPE. I'm quite interested by maybe some of the load to latency. What's the latency you're getting from using the SerDes attached memory? Because I think what you did is a great way to break free from the constraints we have from the DDR bus today. But obviously, you need to have that serial memory controller under the DRAM interface. And people would say, well, a DDR stack on gamer's machine, you'll be in the, 50, 60 nanosecond, but load to use latency is actually much higher than that. So I'd like to hear what you guys are saying with your SerDes driven architecture.
Yeah, so it's you're right. That's one of the major considerations with something like this is the latency as well as the fact that you're burning that I/O power. It's hundreds of nanoseconds, well below a microsecond, and I mean if you're sending uncongested, well below that. But that was definitely a consideration when we did it. And that was when I said we had a custom design protocol. It was designed to help reduce that to the extent we could. But right, it's definitely higher than a DDR4.
And I don't want to neglect it. I think it's a good idea. It just needs to be further improved. And one last question, the chip. So you say the memory interface is 12.5 gigabits SerDes. The whole chip is 12.5 as well, or?
You're asking the SerDes rate?
Yep.
Yeah, that was 12.5 for the memory.
And for the router chip, I don't think I saw.
That's also 12.5 on this chip. Yeah.
Okay.
Chat at the break.
One last
when it was
question.
architected.
Yep.
Nathan Brookwood, Inside 64. You mentioned that you have to worry about making sure that packets go out in the same order that they came in. And I'm wondering what kind of metadata you have to attach to a packet so that you can make sure that you understand the sequencing before you ship them out.
Right. So I believe we have a patent filed on it, which means you can go look for more details there. But we keep track of which packets are which, and then we have a device that knows for a given packet. And so let's pretend a packet has an ID associated with it, not going deeper into depth than that. But that knows that for various packet IDs, which ones must be in order with the relationship with each other, and which ones are free to be out of order. And it basically keeps track of that, and I'd say look at the patent disclosure for more details.
How do you know which ones need to be kept in order?
So for networking, I don't want to say well understood, but it's well understood. And it's up to the choice of the particular router or switch implementation to decide how fine they go. The simple thing, I mean, the simplest rule is if packets are coming in on one Ethernet interface and they're coming in on a different Ethernet interface, there are exceptions to it, but they don't need to be in order. And like I say, there's still exceptions. If they're in the same interface, coming in on the same thing, then the most pessimistic thing is you say they have to be in order, but there's more refinement you can make. And there's all kinds of networking details that go down to what you would be allowed or not allowed to have out of order.
Okay, thank you very much.
Thank you.
We've got to move on to the next. For the final talk in this session, we have Peter Greenhalgh from ARM. He is a fellow vice president and general manager of Central Technology and is responsible for all product IP, including CPU, GPU, and system. He's been at ARM for 16 years, and for each of his years, he has 1 patent, so he's had 16 patents. He has a degree in electrical and electronic engineering from Heriot-Watt University. The title of his talk is ARM Dynamic. I love words that end in a Q. And it's about intelligent solutions using cluster-based multiprocessing. Peter?
Good afternoon. My name is Peter Greenhalgh. So if we look back to 2013, there are a variety of technologies that were capturing the imagination of the general public. We had everything from wearable technology, smartwatches, voice recognition, new social media trends, and of course drones were coming towards us as well, although hopefully not coming towards us too much. At the same time in 2013, the CPU teams had actually just finished Cortex-A53 and Cortex-A57, so they were stepping back and saying, okay, what technologies do we need to look at next? What emerging trends do we have to pay attention to the market? And how do we look beyond mobile, which obviously is a traditional ground for ARM to occupy, and go beyond into mixed reality, look at autonomous driving that was already kind of on the horizon at that time, specifically focusing on safety. We have a safety track record in ARM going all the way back to our Cortex-R series in the early 2000s, but building on that into the A-class space and the applications processors, and all while concentrating on the efficiency that we must build into our processors. So this led us down 3 avenues. The first avenue was to actually look at our cluster topologies and look at how we go and put clusters together and move beyond just having 4 big cores and 4 little cores, look at how we can address different markets with different multi-core technologies and topologies. The second was to look at how we could get more system performance. And specifically, we needed to go beyond just saying, you know what, we want more IPC, we want more megahertz. Everyone wants that. It's a fairly obvious thing to look for. But also what technologies we could build into the clusters which would help us on the system, what new interfaces we could build that would help us with system performance, how we could get more bandwidth, and really focusing on how we did caching. And finally, like the whole of this Hot Chips conference, you can't move for considering machine learning in some way, shape, or form. And while I would definitely not say that we were prescient and we could see all of this coming towards us, we did have some hints, much like many of the speakers so far in the Hot Chips conference. We did have some hints that it was coming towards us, and so we made sure that our interfaces on our clusters and also some of our instruction technology could actually support more machine learning for the future. What we couldn't ignore was our established technologies. So we have ARM Neon, our Amber, ARM Big Little, Core Link, Trust Zone. All of those technologies were kind of our baseline that we had to build off. So we take the new technologies that we were looking at, and we took all of our established technologies that we had to extend beyond, combined them together, and during 2013 to 2017, we built Cortex-A55, Cortex-A75, and Dynamic, which is the overall cluster topology that wraps these together with the dynamic shared unit. So looking at the dynamic shared unit first, so DSU stands for dynamic shared unit. It's a marketing term, don't shoot me. The key part of dynamic shared unit is that we can actually support different cores within the same cluster with different topologies. So if you're familiar with some of the ARM core technology for Cortex going back for the last 7 or 8 years, we would have quad-core Cortex-A9, we would have quad-core Cortex-A5, A7, sometimes triple-core, sometimes dual-core, sometimes single-core, but ultimately up to 4 little cores or 4 big cores inside of a cluster. And while that was very successful for us, and did, of course, enable the mobile industry to concentrate on octa-core, I think we'll move octa-core aside. We won't talk about that much in this session. We needed to look at actually how we could then mix different core types within the same cluster so that we could look in areas like networking of mixing control plane cores and data plane cores. We also wanted to, for mobile, be able to support maybe 1 big core and 7 little cores. And that's key into the mid-range markets and the low-end markets, where it isn't just about the absolute highest performance, but silicon area is absolutely key. And to enable all of this, what we needed to do was actually consider how we did our caching topology as well. So had we just left with a cluster L2 cache shared across the cores, the problem that we would have had would have been that we would need to put an async bridge in between the L1 and the L2 cache in order to be able to run the cores at different frequencies. Now, clearly, we don't want to put asynchronous bridges in because they cost latency, so 3 cycles out, 3 cycles back. 6 cycles of latency on your L1 cache miss, L2 cache hit is painful, as any microarchitect will tell you. So what we did instead is we said, let's move the L2 caches inside the processors or inside the cores. So every single core has a per-core L2 cache in it. That actually gives us an advantage of some performance. So we've turned the disadvantage of having to have asynchronous bridges into an advantage of getting a reduction in latency and more performance. And it also enables some other cool tricks that I'll talk about, or cool technologies that I'll talk about as we go through this presentation. So first, sort of looking at the overall dynamic shared unit. The dynamic shared unit has support, as you would expect, for multiple different performance domains. So we have, so by performance domains, I mean voltage and frequency domains. Because we can have different core cache topologies, we don't have essentially tags, duplicate tags built in there like we have in previous microarchitectures. Instead, we build a Snoop filtering system in there. We have quite a large amount of local memory, so up to 4 megabyte of L3 can be put inside of the cluster. It's a 16-way set associative L3 cache. And then the bus interfaces, because we have legacy in AXI, we have AMBER4 ACE, particularly in mobile, and we have AMBER5 CHI in the enterprise space and the networking space, we had to support all of the bus topologies that ARM currently focuses on. The other thing we really concentrate on, we'll talk about this a little bit more in a few slides, is actually the ACP interface and the peripheral port. So the ACP interface allows an accelerator to be coherently coupled into the processing cluster. And what we did is massively improve the performance of that ACP interface. So back with Cortex-A53 or an A57 or an A72, we could only support 4 outstanding transactions across that interface. That's now increased to 32. So that makes it much more viable for putting an accelerator on that interface. The peripheral port allows us to have very, very low latency programming into the accelerator that's adjacent to the processor. And that gives us the ability to have a very small granule of offload into the accelerator, get it running, and then put it back inside the core when it's done. More power management features, as you would expect. We can't move for adding more and more power management features to try and deal with that problem. And then there's a variety of latency and bandwidth optimizations, which I'll come on to now. So if we look at latency, obviously latency is a killer for CPUs. You want to be able to minimize your cache latency as much as you possibly can. There was a variety of work that was done inside of the Cortex-A55 core to actually reduce the L1 hit latency. And this is the AGU back-to-back path to 2 cycles. By adding the private L2 into the cluster, we've reduced the latency from 13 cycles on A53 to only 6 cycles on A55. And A73 drops 11 cycles from 19 to 8. So that's a really nice improvement in L2 hit latency. Of course, the L2s aren't very large by the cluster to standard. So of course, you still need to be able to get into the L3. And the cluster L3 is 21 cycle latency for the A55 and 25 cycles for the A75. So I talked about needing to go beyond mobile. And this is one of the areas that we push beyond mobile in DSU. What we did here is we said we're just going to do cache partitioning. So what we have is essentially the 16-way set associative cache that can be divided up into 4 sets of 4-way set associative, 2 sets of 8-way set associative, 4-way, 12-way, whatever you wish. It's obviously just granules of 4-way set. And in this particular example, for infrastructure, we have process 2, which has 2 cores inside of it, process 1, which has 6 cores inside of it, and those are allocated a portion of the L3 cache which is dedicated just for them. What we also do is actually can allocate some of the L3 cache specifically for the ACP interface, so any accelerator that's sitting on the ACP interface gets dedicated access into that L3 cache and doesn't have to worry about pollution from the CPU cores. Another example of this is Automotive. So Automotive ADAS, obviously becoming huge in our industry, really interesting area of design and microarchitecture. In this particular example, we have 4 processes spread with 2 cores in each process, and that allows isolation to improve the deterministic execution of the ADAS threads, which is really key. So when we work with our partners, if you go all the way deep into, say, engine management and stability control, it's like every single cycle matters, and it's extremely key. As you step back up to ADAS, it's not quite as tightly defined and tightly controlled, but it's still important nonetheless. And in this particular case, having the cache partitioning supports this more deterministic execution. Another example is we introduce cache stashing. So we can cache stash either into the cluster L3 or we can cache stash into the private L2. And that was another advantage of having those private L2s, is that you can offload a process or offload a granule of execution through the peripheral port into the accelerator. The accelerator does its work. When it's done with it, can then go and put it back straight into the core that supplied it. And that allows a much faster interaction time between an accelerator and the CPU cores. So here we have one example of offload acceleration, which may be cryptography. So while we support the AES standards natively in instructions inside of the processors, there are many cryptography standards, and you may choose to want to execute them in an accelerator that's adjacent to the core. So in this case, the low latency peripheral port programs the accelerator, accelerator goes, pulls data out of the cluster or the core coherently, and then can return it once it's completed. Not just about cryptography, also about I/O processing. So if you have an I/O processing task, say packet processing in networking, then again, you can use the same mechanism. So it's a capability that nobody in the client space, nobody in mobile or clamshell or whatever will be in general interested in. However, in offload acceleration, particularly networking, then it's quite an interesting technology. And I mentioned safety. Obviously, safety is extremely key in many of our markets now, very much so, obviously, in automotive, particularly with autonomous driving coming towards us. So what we've did when we designed the DSU is enabled it with capabilities that allowed it to be used in an ASIL-D capable system. So if you want to go all the way through to the ASIL-D requirements that you have in autonomous driving at the moment, then it's key that the IP that you have from ARM or from any other IP vendor, plus everything that you build yourselves, can be certified to an ASIL-D level. And therefore, we designed DSU with that capability in mind. In particular, what we also focus on is that there's, and ARM often says this, it's not one size fits all. You need to use the right processor for the right job. When you go all the way out to the sensors are usually an M-class based processor. As they come through the applications processor for perception, so the perception calculations performed on the applications processor, and then all the way through to the R-class processor, which we call actually a safety island, then performs the decision and actuation, say the braking system or the stability control. So that's DSU. Moving on to A75 and A55, because I realize as a Hot Chips conference, you're probably interested also in wider CPU microarchitecture. So we will step through to a degree the A75 and 55 microarchitecture. Before I go there, I'll give you an idea of the performance uplift compared to the previous generation. So the predecessor for Cortex A75 was Cortex A73. The predecessor for Cortex A55 was Cortex A53. Compared to their predecessors, we're seeing around 20% performance improvement in SpecInt 2006 and anywhere up to 40-odd% improvement in SpecFP 2006. The classic benchmark of the mobile world, Geekbench, we're looking at 34 or 21% uplift depending on A75 or A55. But A55 in particular concentrates a lot on its memory system. So it's a huge amount of work done by the microarchitecture team on the memory system and actually doubles LMbench performance. And just to say, there's no tricks here. This is all exactly the same frequency. There's no process in here. There's no any trick like that. It's purely IPC and purely performance benefit on a clock-for-clock basis. Looking first at the architecture and pipelines, both of the microarchitectures are an ARM v8.2 based implementations. So both of them implement the entire ARM v8.2 instruction set and all of the extensions. Both of them obviously can reside inside a dynamic cluster. However, Cortex-A75 is obviously a performance-focused microarchitecture. It's 11 to 13 stages. It's an out-of-order pipe. Whereas A55 is more focused on efficiency, much like the A53 and the A7 and the A5 before it, and it's an in-order 8-stage integer pipeline. Walking through the pipe, if we first start the instruction fetch, both have a 4-way set associative cache, both are VIPT. Both of them have instruction queues of differing natures to decouple the fetch side of the design through from the execution core. For the A75, because it tends to go in very high-performance applications, the instruction cache is only 64 kilobytes because actually the size of the L1 cache in comparison to the overall call is, it doesn't matter quite so much by the time you get to these size of cores. 4-wide instruction fetch, so basically 128 bits. For the people who then point out of thumb16, that doesn't mean you can that we're suddenly processing 8 thumb16 instructions per cycle, but we can fetch that many, of course. A55 is more flexible, as you would expect from a little core, so you can have different cache sizes, 16K through 64, and it only has a 2-wide instruction fetch path. Branch prediction, actually the Cortex-A73 that preceded the A75 had a really good branch predictor. It used a table-based conditional prediction, and it was good enough that while there were some tweaks on the branch prediction, there was no need to go and redesign another one. However, a zero-cycle prediction, so to be able to get that very fast turnaround to minimize loop bubbles in your pipe, was clearly an area to pay attention to. So the A75 team did improve the zero-cycle prediction capabilities compared to A73. On A55, the predecessor A53 didn't have actually a zero-cycle prediction capability, or at least not one that was comprehensive. So consequently, the team went and designed zero-cycle predictors in there to cover conditional branches. Obviously, it has a BTB in there, core return stacks, all of the things that you would expect inside of there, but focused on zero-cycle prediction. And then there was a completely new conditional predictor in there. Again, everyone's talking about neural networks, so we'll chuck that one in as well. It's a neural network-based conditional predictor. And then loop predictors, as you would expect, to be able to build in there to improve the prediction capabilities. The core's obviously very different. You've got an out-of-order core with A75 and an in-order core with A55. The out-of-order core, it's a 3-wide decode machine, so obviously 3 decoders. Can spit out multiple micro-ops, so it can crack micro-ops out of those decoders, so it's not 3-wide through 3-wide on the other side and dispatch. From an issue perspective, it's a 7-wide issue machine, 2 ALUs, 2 load store pipes, 2 neon float pipes, and a branch pipe. So in theory, when all the stars align, you can get 7-wide issue, but as we all know, that is the uncommon case. And there was a lot of effort put into the memory system to increase the L1 miss, L2 hit performance, and also to increase the out-of-order window and having more outstanding loads in flight through to the L3 and then on to DDR. A55, quite simple by comparison, builds on the tried and tested Cortex-A53 pipeline. And what we've done here is the design team took the A53 pipe, which was limited to only a load or a store per cycle. Now it can do dual issue of loads and stores, concentrated very much on latency. So a lot of the work that was gone on in the pipeline was to improve instruction execution and decrease latency, because obviously that always pays for itself. And then worked on, as I say, reducing this L1 cache load to use latency for pointer chasing. L1 memory system, again, as you would expect, a big out-of-order core will have a quite different memory system from an A55 with the in-order core, but obviously the details of it are perhaps beyond this conversation. Common features are a four-way set associative L1 data cache in both cores, and again, the same reason that there's only a 64K instruction cache on A75, there's only a 64K L1 data cache on A75. Load store capability was increased, so the load buses could actually go up to 128-bit if necessary, which was an improvement or an increase over A73. And there's a greater capability for reordering, so the read after write filtering capability that was added into there. Moving to A55, again, flexible on the L1 data cache, so having this 16K, 32K, 64K capability was very useful to be able to tailor it to different markets. The store buffer bandwidth was increased into the L1. Obviously, the store buffer is quite a key part of that design to be able to make sure that there aren't any blockages, particularly when you start factoring in ECC and read, modify, write, and everything you have to be able to do inside of that part of the design. And then the TLBs were increased. The TLBs were actually increased across the L1 level all the way through the A55 and A75 cores, just because that always pays for itself by having a larger TLB capability at the L1. In the L2 memory system, both have a private L2 cache. Both of the L2 caches run at core speed, which is really quite useful, but obviously puts a lot of timing pressure on the input path into the L2 cache and the output as well. So it's a one cycle into the L2 cache, it's 2 cycles out. Fairly clearly, it has to be fairly quick through there because our overall L1 miss L2 hit latency is very low. We have the cache stashing capability into the L2. And then the main TLBs were increased in size dramatically. So we doubled in size from 512 entries with A53 and with A73 to 1,024 entries. Both of them use non-blocking schemes, so if there is a hit and a miss, they can actually keep on making progress, so that outstanding miss can go on. Obviously, that helps far less in the case of an A55, where ultimately, because you've got an outstanding load that's missed a TLB request, then you are going to stall behind the pipe very quickly after that, but it still allows you to get moving very quickly after the stall unblocks. L2 cache size, 256K or 512K on the A75, and then on the A55, you can remove it altogether, because again, we have to be able to address a wide range of markets, and there will be some markets that say area is absolutely king, I need to take it off. But it can go all the way up to 256K. Architecturally, there were some quite nice new features that came in with ARM v8.2 compared to the ARM v8.0 that was the A73 and A53. So we had a dot product instruction that has come in and half precision float, again for AI and ML. Compared to Cortex A53, we're looking at about 5x performance improvement on machine learning kernels. It's an 8-bit data type, so 8-bit integer data type that we focused on there, which is obviously very key for inference engines, or very popular, should I say, for inference engines. But we also have the FP16 capability as well, so half precision floating point if that's your poison. Virtualization host extensions were added as well, which allows the Type 2 hypervisor performance to be improved. And then some of the other architecture features that came in, like cache stashing, atomic operations, which came in with ARM v8.1, cache clean to persistence, and then infrastructure RAS. So these are all part of building the story around being able to put an A75 credibly into infrastructure, into networking, into server use cases by having not just obviously the pipe and the IPC and the megahertz, but all of the other things that you need to be credible in that market. So in summary, the compute landscape changed between 2013 and 2017. I think we all saw it to a greater or lesser degree. We needed a new cluster topology. We've managed to build that. We've also, actually, it's a massive endeavor by the design teams to actually build concurrently 2 CPU microarchitectures, the A55 that was built out of our Cambridge design team, and then the A75 that was built out of our Sophia Antipolis design team. And then the DSU, which was also built out of Cambridge. But like all these things, they leveraged our Austin Design Center, our Bangalore Design Center, so it really was an international effort to be able to put all this together. And we had many, many, many hundreds of people working on the A55, the A75, the DSU, the verification, the system analysis, the benchmarking, everything that we needed to do to put these processors together. And incredibly, they actually arrived within a week of each other into a few of our lead partners who then rushed them through to tape out. We're super pleased that actually there is some sample silicon back for these processors, and it's working great. And yeah, DSU DSU A55, A75 is a great new technology, and we're really pleased to present it to you all. Thank you.
Questions on the right.
Hi there, Rob Nertney from Xilinx. Just had a quick question regarding the cache stashing. Is that just like an instruction that basically makes a portion of the cache essentially memory mappable, or how do you end up saving stuff and stashing with this instruction?
Essentially, it's a hint that comes through the bus interface, which tells the CPU to go and prefetch from that address. So what happens is, say you've got an accelerator, and the accelerator says, right, I'm done with this workload, and you know where it is in memory, so it then goes and says to the CPU, go and fetch this from memory. Because it's all coherent, it then goes and pulls it out and drops it into its cache.
Okay, thank you.
On the left.
Hello. Hi, Michael Shea. The question here is, in the context of processing data at the edge, is there any feature in this architecture that has been included to accelerate user software application?
Well, there's raw IPC in the pipeline. So in terms of processing performance, if I understand your question correctly, in terms of improving the performance of the microarchitecture at the edge where the user is using the device, both microarchitectures have improved in performance by 20, 30, 40%, depending upon what your benchmark is. So fundamentally, the microarchitecture has added those features. So A73 was a 2-wide decode machine. A75 is so A72 and A73 were 2-wide decode machines. A75 is a 3-wide decode machine. So that itself increases the bandwidth, and there are many other parts of the microarchitecture. So don't know if that answers your question, but.
That's okay, I'll get offline with you.
Okay.
Thank you.
Nathan.
Yes, with regard to both the A55 and 75, what are you doing with regard to cache management? Is it right back, right through at L1 and L2?
Oh, they're right back, right to allocate caches.
They're all right back in all those cases?
Yeah. We don't use right through. It is used by some partners, but we're right back, right allocate, except for when you start going into a streaming case. And then when you're streaming, obviously, you just go into a read allocate mode because you don't want to start polluting your cache.
Better for power management that way, I suspect.
Yeah.
I assume all the write-back caches are ECC protected?
Of course.
Yeah.
Hi, Zay Samuels from Samsung.
Hi.
Can you elaborate on the L2 latencies? They seems relatively low. Is that like a low tiers latency? Does it include L1 lookup?
Yep.
Is it at all sizes of the L2 at all frequencies?
Correct. Yep. So all sizes, all frequencies. So go to peak frequency, and you do, and it's all the way. It's the AGU loopback path. So start at the AGU, go through the L1 addressing, L1 output. You've then missed the L1, drive across to the L2, L2 tag lookup, L2 data output, 2 stages of that because it's fairly large.
All at
then then do all of your rotation alignment, all of the usual fun, and then send it back into the AGU. So that's purely AGU to AGU loopback. So yeah, it is fast. There was an awful lot of effort put into making that path as fast as possible.
Do you wait for L1 hit-miss determination before you proceed?
Yeah, we don't. There obviously are techniques you can use if you're less concerned about power, and that's not to say that's a bad thing. There are certain cases where you would sacrifice power for the performance. But yeah, we make sure we look up in the L1, and if we've missed, then we go to the L2. We don't speculatively look up in the L2.
Within the 8 cycles?
Yeah.
Thanks.
Let's take one last question on the left.
Andy Glue for it last. I could ask a lot of questions. I'll just stick with one. The atomics are in the instruction set. How are they implemented? Are they exported and done outside the processing elements, like on a GPU? Or are they done by pulling the data into the GPU?
No, all of the atomics are inside the CPU. They're architectural instructions, so you can go and look them up in the
I have, but you can implement them outside or inside.
well, there is a notion of far and near atomic, but ultimately all of it is controlled by the CPU. The details of what's going in the system, I couldn't tell you.
Do you have a bus transaction that does the atomics?
Do I have a bus? No.
Thank you, Peter. As is tradition at Hot Chips, the last afternoon break on the second day is an ice cream break, so enjoy the ice cream and please be back at 5 o'clock for an exciting final session. Thank you very much.